Welcome back. Today we'll graph polynomial and rational functions. Now remember, when we consider the domain of rational functions, we're looking at the denominator. The denominator will make the restrictions on the domain. So usually it's all real numbers except for any value that makes the denominator equal to 0. Now when we're looking at the zeros, the x-intercepts, that's when we have to set the numerator equal to 0. Now let's consider some of the asymptotes. Now the vertical asymptote is as x approaches the value a, f of x will either go to positive infinity or towards negative infinity. So here we have an asymptote. I'll put, so on the asymptote, we're going to have the function as it approaches the asymptote, it goes towards positive infinity, or from the other way, as it approaches it from the right, it'll go to negative infinity. Now a horizontal asymptote is a little bit different. So a horizontal asymptote, it means that when x approaches positive or negative infinity, then the value will be closer to b. So I'm going to use the same picture, but now I'm going to sketch a horizontal asymptote. So you can kind of see with this graph that as x is approaching negative infinity, it's getting very, very close to that line, that horizontal asymptote. And as x approaches positive infinity, it's again getting very, very close to that line. Now, to determine the equation of the horizontal asymptote, now let's look at the value of n, the degree of the numerator. When it is less than the degree of the denominator, represented by m, the equation of the horizontal asymptote will be y equals 0. If the degree of the numerator and the degree of the denominator are equal, then the leading coefficients, that quotient or ratio, will determine the equation of the horizontal asymptote. Now, if the degree in the numerator is bigger than the degree in the denominator, there will be no horizontal asymptote. There may be a vertical, but not a horizontal. When the degree is actually exactly 1 degree higher in the numerator, there will actually be a slant asymptote. You could also say oblique asymptote. So whenever we want to figure out that equation, we're going to use long division. And that quotient will give us the equation, y equals the quotient. It doesn't matter actually if you have a remainder or not. We're not going to consider that remainder. But the quotient will be the equation of the slant asymptote. Okay, key things to remember whenever we're talking about rational functions. The graph of a function may cross the horizontal asymptote or the slant asymptote, but it'll never cross a vertical asymptote, because that's when the function would be undefined. That's when the denominator would equal 0. The graph can have more than one vertical asymptote. A graph can only have one horizontal asymptote or one slant asymptote. Now remember, to determine if it has a slant asymptote or a horizontal asymptote, we're looking at the degree. Right? So the degree, there's going to be a comparison. So it'll either be greater than, equal to, or less than. We can never have both or more than one situation. So that's why there's never more than one horizontal or slant asymptote. Now let's look at some of these problems. For each of these, we're going to find the domain, the zeros, and the asymptotes. So for the first one, well, let's first find the zeros. So when we want to find the zeros, we're going to set the numerator equal to 0. And you can see it's going to have a multiplicity of 2, right? Because it was x squared. Well, we can consider and figure out the y-intercept because the x-intercept and the y-intercept will be the same. So it's going to intersect at 0, 0. That's also the y-intercept. Now for the vertical asymptote, we're going to set the denominator equal to 0. And we want to say the denominator can never equal 0. Well, when I subtract 1, you can kind of see that it doesn't matter what I do or plug in for x, it'll always be positive. So for this equation, there are no vertical asymptotes. Now let's look at the degree. So if you look at the degree, we have an x squared in the numerator and an x squared in the denominator. So this tells us that the n, the degree of the numerator, equals m. So the equation of the horizontal asymptote will be the leading coefficients, which is just 5 over 1. So it would just be y equals 5. So when I consider the domain, well, we know that this function doesn't have any vertical asymptotes. So there's really no restrictions on the domain. So I could write the domain as all real numbers. Now let's look at the second one. 1 over x plus 3. Well, you can see right away that if we were going to try to find the zeros, there would not be any because 1 does not equal 0. We set the numerator equal to 0, so there'd be none there. And if we plugged in 0 to find the y-intercept, that'd be 1 over 3. Now let's look at the denominator. So for the vertical asymptote, we set the denominator not equal to 0. So we know the vertical asymptote is going to be x equals -3. So it definitely has a vertical asymptote. The degree in the numerator and the denominator are the same, or sorry, is greater in the denominator. So I'm going to put that the degree in the numerator is less than the degree in the denominator. So we're going to have a horizontal asymptote at y equals 0. Since there was a restriction on the domain, on the vertical asymptote, our domain is going to have 2 intervals. So we can go from -infinity to -3, because that's where the vertical asymptote is, and -3 to positive infinity. Now let's look at this rational function. We have 3x in the numerator, and then we have a quadratic in the denominator. All right, so I'm going to first factor just to make sure we're able to see this clearly, okay? So that's x squared, so that's going to be x plus 2, x minus 2, or x minus 1, excuse me. All right, so we know that right away it's going to have 2 vertical asymptotes. So we could say x equals -2, it will be 1. And then make sure you write an equation for the second asymptote. X equals 1. So this one has 2 vertical asymptotes. When we look at the degree is bigger in the denominator, less in the numerator. So the horizontal asymptote will be y equals 0. Now let's look at the zeros. So for the zeros, remember we set the numerator equal to 0. So that's just going to be x equals 0. And if we plugged in 0, right, for our function, you would know that the y-intercept would also be 0, 0. So we have the zeros, we have the y-intercept, we have 2 vertical asymptotes, and 1 horizontal asymptote. Now these vertical asymptotes are going to make the intervals for the domain. So it's going to go from negative infinity to negative 2. It can't be negative 2. The second interval is negative 2 to 1, not inclusive. And the third interval is from 1 to positive infinity. Now let's look at this one. X squared plus 1 over x minus 2. You can see in the denominator that there's going to be a vertical asymptote right away. So we know that x minus 2, we set that equal to 0, the denominator, so x equals 2. Now, if we look at the degree in the numerator is bigger than the degree of the denominator. So there is no horizontal asymptote. There will be a slant asymptote because the degree in the numerator is 1 degree higher. So for the slant asymptote, we're going to have to use long division. So we're going to divide x squared plus 1 and divide that by x minus 2. Now when we multiply x by x, well, we get x squared. So this will be x. And let me just delete this thing here. And we'll have x squared minus 2x. And when we subtract, we'll get, this will be 2x. I'm going to bring down the 1. And we need to multiply this by negative 2, or positive 2, to get 2x again, right? So this is 2x minus 4. And the remainder is irrelevant. The equation for the slant asymptote is y equals x plus 2. Now let's look at the numerator for the zeros. So remember, for the zeros, we set the numerator equal to 0. But you could probably tell right away that x squared will never equal negative 1. So there are no x-intercepts. To figure out the y-intercept, just plug in 0, and you'll get 1 over negative 2, or negative 1/2. So the one thing that we want to make sure, remember, we have to look at for the domain is the vertical asymptotes. So the domain is just restricted by the vertical asymptote. So it would be negative infinity to 2, and then 2 to infinity. Now let's consider the last one on this page. So remember, we always want to try to factor whenever possible. So x squared minus 4, that's a difference of squares. So that's x minus 2, x plus 2. And then in the denominator, we actually have x minus 2. So that we have this common factor, and that would cancel out. And we're left with the function x plus 2. But remember, our restriction would have been x cannot equal positive 2. Now what does that mean? Well, that means that we're going to have this graph with a slope of 1, right? And a y-intercept of 2. So we can figure that out. Let's see. So this will be 2 right here. And we could kind of make a sketch here. We could probably figure this out really quickly, but this slope right here is 1. The y-intercept would be negative 2. See if I can draw a line there. Okay. It's a little off, so I'm just going to fix that. Okay, so there's the line, there's the function. But remember, we had that caveat here that this would not be able to equal 2. So what would that point be? Well, if we plug that in, that would be approximately 2, 4, right? If I plugged in f of 2, we would just get 4. But remember, x cannot equal 2. So this point, 2, 4, is actually called a point of discontinuity. So I'm going to put a little circle, an open circle, where that point would be, and continue the line through or around that point. Okay, so that point is a point of discontinuity. We know that that's going to be a restriction on the domain. To approximate it, we just plugged it in. So we just evaluated f of x for that point of discontinuity or hole. So that's going to dictate the domain. So the domain will be negative infinity to 2, and then 2 to infinity, not including 2. You can tell very quickly that this function does not have a vertical asymptote. It does not have a horizontal asymptote. And even though the degree is 1 degree higher in the numerator, this does not have a slant asymptote. It reduces to the equation of a line with a hole. Now let's consider how to sketch a graph of a rational function. Whenever we sketch a graph, we want to make sure we simplify the function as much as possible, because we may have an example or a graph just like the example that we covered with the line. So if you can reduce it, try to reduce it as much as possible and see if there are any holes. Next, let's plot the y-intercept. That's probably the fastest to find. And then you want to find the zeros by setting the numerator equal to 0. When we set the denominator equal to 0, we'll be able to find the vertical asymptotes. And then we want to figure out, is there a horizontal asymptote or a slant asymptote? Lastly, plot points between the x-intercepts and the vertical asymptotes. Sometimes you just need to see if they're positive or negative. And then to sketch the graph, just make sure you use smooth curves, not jagged lines, for rational functions. All right, let's sketch this graph. 2x plus 1, x minus 3. So when we consider the zeros, we're going to set the numerator equal to 0. So we know that 2x plus 1 equals 0, so x must equal negative 1/2. Now let's find the y-intercept. So f of 0, when you plug in 0, you'll just get 1 over negative 3. Now let's look at the vertical asymptote. We set the denominator equal to 0. So we know that we're going to have a vertical asymptote at x equals 3. And because the degree is the same in the numerator and the denominator, the equation for the horizontal asymptote will be y equals 2. So let's sketch what we know. We know that we have a vertical asymptote at x equals 3. We know that we have a horizontal asymptote at y equals 2. And then we actually also found 2 of these points. So we know that at negative 1/2, which is about here, and negative 1/3, about there, that's the y-intercept. So we know that this section of the rational function will stay, remember, it cannot cross a vertical asymptote. So it must stay in that corner and be a smooth curve. Now to double check, we always want to double check, let's plug 4 in there and see what we get. So when we plug in 4, well, we get 8 plus 1, that's 9 over 1. So that's 9. So this is going to be up here, probably very high. And remember, it's going to get very, very close to the asymptotes, but not cross. Now let's go to the next one. Whenever possible, remember, we want to try to factor whatever we can. So that's going to be an easy factor. So that's going to be x plus 4, x minus 1. All right, so let's look. So zeros, I'm going to write this down, but you can see that the numerator can't equal 0, so there's going to be none. For the y-intercept, if I plug in 0, I'll get 1 over negative 4. Now we know, and we can see right away, that there are going to be 2 vertical asymptotes. X equals negative 4 and x equals 1. Remember, we're writing 2 separate equations. The degree is bigger in the denominator, so the horizontal asymptote will be y equals 0. Okay, let's sketch what we know. So we know we're going to have a vertical asymptote at negative 4. We're also going to have another vertical asymptote at x equals 1. And you can kind of see it in the red, but we know that we'll have a y-intercept at 0. Now, when we're graphing it, we want to make sure we graph some points. So I'm just going to make sure I graph points beyond and in between the vertical asymptotes. So I'm going to try negative 5. I'll try negative 1. Let's see, that should be good. And then we have 2, because that other y-intercept was 1. Okay, so when I plug in negative 5, I'm plugging into it's kind of easier to plug into the factored form. So that's going to be 1 over negative 1 times negative 6. So that's going to be positive 1/6. So that's going to go like that. It'll follow the y-axis, I'm sorry, the x-axis and the vertical asymptote. When I plug in 1, we get 1 over 5, negative 2. Oh, sorry, that'll be 3. Let's type that in. And then we'll have, that's also, well, that's going to be negative 1/6. So that's going to be down here. And we actually already have the y-intercept as well. So that'll be about here. So we can imagine that this part of the graph, and let me just draw that a little bit more cleaner. Will stay below the x-axis. And the last point is 2, so that's going to be 1 over, that'll be 6. Again, that'll be 1/6. So that's going to be up and to the right. Okay, so we always want to plug in some points, and they don't have to be exact. You're just really looking for if they're positive or negative, especially when you know that the y equals 0 is a horizontal asymptote. All right, let's look at this f of x equals 2 over x plus 1. Well, you can see right away that you're going to have a vertical asymptote. And you can probably see right away that there's not going to be any zeros. If I want to find the y-intercept, I'll just plug in 0 here, and that's going to equal 2. So the equation for the vertical asymptote is when we set the denominator equal to 0, so that'll be negative 1, And we know that the horizontal asymptote will be y equals 0 because the degree is bigger in the denominator. So let's just graph this. Here's the horizontal asymptote. Here's the vertical asymptote. Makes those 4 quadrants. We already know one point. We know this is going to be 2. So we know that this part of the graph will be on the top right. And just to verify, we could just plug in another point. We could plug in maybe -2. So that'll be 2 over -1, which will be -2. So that's down here. Notice that it'll be a smooth curve and the functions will get very, very close to those asymptotes. Now for D, make sure that we, again, factor whatever we can. So this denominator, 2x squared plus 5x, well, that's going to be 2x minus 1 and x plus 3. Right, 2x minus 3. And so that we get 6x minus x. All right, so right away we can see that we're going to have a 0. So we can say, well, set that equals 0. So the 0 will be at x equals -1. To find the y-intercept, we're going to plug in 0. So that's just going to be 1 over -3. We can see that right away we're going to have 2 x-intercepts. We set each of those equal to 0. So x will equal 1/2 and x will equal -3. Writing 2 equations. And then we know we're going to have a horizontal asymptote because the degree is bigger in the denominator. So that's y equals 0. All right, let's graph what we know. So here's one vertical asymptote. And that's going to be 1, 2, but the second one will be at 1/2. And then I'll just make sure I put the horizontal asymptote, even though it's already there with the axis. Okay, so we know that we have the 0 at -1. We also have a y-intercept at -1/3. So there's a couple points that we need to make sure we plug in. So I'm going to make a little table up here. We definitely want to try something to the left of -3. So -4. And that'll be -3 over -9 times -1, so that's +9. So this is going to be -1/3. So we know this part on the left go down because that was negative. We could try -2 because we want to see, does this touch, or, I mean, it's going to probably go through because it has a multiplicity of 1. But I just want to make sure. So we plug in 2 and we get -1 over -5 times 1. So that's going to be just 1/5. So that's up here. So this part kind of looks like a cubic. And then I'm going to try one more point to the right of 1/2. So just try 1. And when we plug in 1, we get 2 over 1 times 4. So just 1/2. The graph will be on the top right. Okay, for E, we can see right away that we're going to have a vertical asymptote and some zeros. So let's start with the zeros. We set the numerator equal to 0. That's a 5. So we have x squared equals 5. So we'll have plus or minus root 5. To find the y-intercept, we're going to plug in 0 for x, and that's going to be negative 5 over 2. We can see right away we have a vertical asymptote at x equals negative 2. And this will probably have a slant asymptote because the degree is bigger. So there will not be a horizontal asymptote. And to find the slant asymptote, we're going to have to divide x squared write that clearly, x squared minus 5 by x plus 2. So we can see right away, well, that'll be an x. And this is negative 2x. And we're going to have to multiply this by negative 2 to get to negative 2x. So there's our equation. And remember, the remainder is irrelevant here. But the remainder would be negative 1. So the equation, I'll write this in a different color, for our slant asymptote is y equals x minus 2. All right, so let's graph some of these things. So we know that we have a vertical asymptote at negative 2. We also know that we have a slant asymptote. I'm just putting the y-intercept there, but we know that it's going to have a slope of 1. So it's going to go like this. And I'm going to extend this a little bit further because we want to see what happens down here. Okay, so looking at this, we definitely can see right away that there's going to be 2 x-intercepts. And root 5 is a little bit more than 2. So there's going to be 1 here and then 1 here. So we can test some points, but we also have the y-intercept at negative 2.5. So we know that this part of the function is going to get very close to the vertical asymptote and the slant asymptote, but stay in the bottom right. And we know that this part on the left will be on the top left because it has to go through the x-intercept. Well, I hope this lesson was helpful, and I'll see you all in class.